Hello everyone, we are back at Computer Vision Talks after a long break of a month, and today we have with us Francesco. Francesco is a postdoc at the Center for Intelligent Imaging at UCSF in Valentina, Pedoia's lab. They are active in the domain of machine learning and deep neural network architectures applied to medical image analysis. This is going to be our first paper in the domain of medical imaging, and we are really excited to it. He received his PhD in computing from University of Lincoln in UK, and his thesis was centered around a fluid dynamic approach to extract vascular trees in fundus photography. And he's got lots of research experiences. During his master's, he visited Keio University in Tokyo, which was focused on lab on chip for liver tissue engineering. And we're looking forward to your talk, Francesco. Please go ahead.
Thank you so much for the introduction. It's very kind, especially the invitation to be here today. It's a great honor for me. And today, during this presentation, I would like to show that it's possible to segment accurately cartilage from knee MRIs, even if we use highly undersampled MRIs or highly accelerated. And also what I want to show is that the quality of this segmentation will be comparable to that can be obtained from state-of-the-art approaches that are designed ad hoc for segmenting fully sampled MRIs. So here an overview of today's talk. I would like to show first the motivations behind accelerated MRI. Then I will present some state-of-the-art approaches and what is the role of deep learning in the context. I want to describe some common limitations of the current image reconstruction approaches and some possible solutions to these problems. And then I will show fast MRI from a slightly different perspective, where I will discuss some of the work I've been doing in the lab about task-based image reconstruction. So since you said that not everyone here has been working in medical imaging, it's good to have a bit of an overview of the application of deep learning in medical imaging. And it has found since the introduction of CNNs, deep learning has been widely utilized in medical image analysis. And there are, I would say, probably three main categories that could group the application of deep learning in this domain. The first one is image analysis, which includes subtopics such as feature extraction, tissue segmentation, or detection. And then we have a second application, which is diagnosis, which can partially rely, but also not necessarily on the first step. In fact, for instance, we can extract some features or we can segment some tissues. And then we can perform classification, make decisions, or monitor, for instance, the progression of a disease. So if we have segmented, let's make a couple of examples. Let's say we segment knee cartilage from some MRIs, then we can monitor the thickness over time and decide whether a patient is developing osteoarthritis, or if we segmented the retinal vessels from a fundus photograph, we could potentially analyze if the patient is progressing to diabetic retinopathy by, for instance, quantifying the angles at vessel branching points. And then there is the third group of applications, which I'm mentioning now at the end, but in reality, chronologically comes before the image analysis and diagnosis, which is the image generation. And this includes all the pipelines that go from the acquisition that happen at the scanner level and that eventually lead to an image that is utilized by the radiologist. And if for many years, deep learning or machine learning in general was not playing a big role in this part, recently is a very active topic of research for the machine learning and deep learning community as well. And this part, which is the application, also includes themes such as the image acquisition, since we need to acquire the image, and the image reconstruction step, which are all the algorithms that are used to move from the raw signal that is acquired at the scanner to the image that then is analyzed by the doctors. And or otherwise, there is artifact corrections, since most of the organs are not still, or super resolution, where some images are initially acquired at low resolution. And the goal here is to form images which have a much higher resolution. And the topic of this research will be focused mostly on, of today, or the presentation will be focused on the image generation. And what you will see that I will try to show the work that we did, where we are connecting the image generation with also image analysis with what we call task-based reconstruction. So let's put everything into context with a practical research question that we might tackle in our lab. And for instance, we want to learn some features from some MRIs, and we want to use these features to diagnose and predict osteoarthritis, which is a very debilitating musculoskeletal disease. And soon we can find two main issues to solve this task. And first is that we need availability of high resolution MRIs. And second is the accurate tissue segmentation, which in turn cause that we need to annotate the data. So this requires expertise and is also expensive, but as well we need long scan time for the acquisition per se. So what could be potential solution to these problems? Here on the left, I'm showing what it's called K-space, which is the raw image of the that is acquired the scanner. And soon, in the next few slides, we also be clear. So what happens is that one of the possibility is to, if we want to accelerate the acquisition, because we said it's one of the problems is the acquisition time, we could accelerate the MRI. And therefore, one of the ways we could accelerate this problem is just by reducing the acquisition time. On the other hand, we could also think to automate the segmentation. And here on the right, I'm showing you a fully sampled MRI. This is a sagittal view of a knee. Yes?
One question. Would you like questions in the middle, or should we put it in the end?
We can, I don't know, up to you. I mean, if you think that there is a question that needs to be asked, otherwise it's impossible to continue, I'm happy to take it, otherwise at the end.
Great. So can you please put some more light on this fully sampled MRI? What is fully sampled? Like, what do you mean by when you use the term fully sampled or unsampled?
Okay, it's something that I'm going to explain in one slide. But anyway, what happens is that if you can see this yellow line in the animation, basically the MRI are acquired in a space which is the domain, the frequency space, and or also in the Fourier space. So what is this image represent different frequencies. So what happens is that in order to create an MRI, all the frequencies need to be acquired, and this is done sequentially. So you traverse sequentially this K-space. So when I say fully sampled, it means that all the frequencies in this domain have been acquired. Whereas when I will mention about undersampled, means that some of those frequencies have been not acquired.
Understood. Great. Please go ahead.
So when you have an image that like a K-space that has been fully acquired, you have an image like this, where on the outer part of the K-space, you have information that relates to edges and sharp details of the image. Whereas the inner rows of the K-space have mostly general information about the contrast in the image. What it means is that every point in K-space has information that belong to, related to every other pixel, for instance, in an image. Because that frequency spreads across the image. So if there are high frequencies, then we contribute to every part of the image, of the MRI image. Does this make sense?
It does. So K-space contains information, and the outer edges of the image has information about the edges and texture. Is that right?
Exactly.
And in the center, the information is about?
it's about more about the contrast and the contrast of that you have in the image.
Understood.
So whereas we can accelerate the MRI, we can also think about accelerating the process of segmenting. So instead of doing it manually, we could automate the process. And this is this is an example where we have a fully sampled MRI and the yellow area that I am showing here is the menisci. And it is pretty easy to automate the segmentation on a fully sampled MRI. What happens is that if we instead decided to accelerate the MRI, for instance, by taking every other line of the case space, the image that we would obtain is no more as nice as the one I showed earlier. So if we try to segment an image like this, the quality is no more as spectacular as we showed earlier. And this shows that it's important to have a system that both can accelerate the acquisition, but as well provide accurate segmentation from images that have been acquired in accelerated settings. So at this point, I would like to show you why the MRI is low in the first place, which is what I already told you very briefly. So we have the MRI, which is a machine that has been designed to screen the Fourier transform of the images that you are observing. So to do so, as I said, we acquire sequentially the case space. And then, because there is a relationship between the image and the case space, it is possible to apply an inverse Fourier transform and go to the image that is the image that a radiologist usually look at. And if we started from these images and we applied a Fourier transform, we could go back to the case space. So this is a very important point. The Fourier transform is the operator that allows mapping from case space to image space. And because we are acquiring sequentially, this is obviously the bottleneck in the acquisition. So if we instead thought about accelerating by skipping every other line of the case space, what can happen is that the image doesn't look anymore as nice as we were expecting. Because what happens is we are violating the NeurIPS theorem, which is a theorem that is related to the generation of a signal from a limited number of samples. And what happens is that we obtain an image that has these enfolding artifacts. So obviously the question could be, can we still obtain good MRIs if we are starting from limited number of data? And the answer is yes, and there has been a lot of research going on recently, but in the past few years. And there are different type of approaches. Some are are called constrained reconstruction approaches, like compressed sensing, which utilize some, rely on some transform sparsities, or low rankness methods where the case space information that is missing is modeled by using local neighborhood, or other approaches which are data driven, which are based on deep learning. So I will first introduce one of the constrained reconstruction approaches, like this compressed sensing, since this will be useful because there will be one experiment later that uses compressed sensing. So it's good to understand what it's about. And the other approaches are deep learning based, and I will discuss them soon after. So compressed sensing, which is an approach, an optimization based approach for image reconstruction, relies on three main principles, which are incoherent subsampling, transform sparsity, and nonlinear iterative reconstruction. So I want to show you in a practical example of an MRI of an apple, which is an example I really like, how this component help the reconstruction. So let's start with incoherent subsampling. And what it means is that, okay, sorry, here first you see what happens if we have acquired a fully sampled MRI. So that would be this section of the apple that we would see in this MRI. And sometimes though, while for an apple, we can keep an apple still for a long time, this might not be so easy, for instance, for organ, let's say, the heart is beating, the lungs move while the patient is breathing, and it's not so easy, for instance, to us to stay still for a long time. So with respect to compresensing, the first help comes from when we want to undersample, it comes from this component, which is the subsampling, which means that we acquire less data. And let's say that we can, for instance, tend to acquire mostly the data from the internal part. So we have most of the information coming from the image. But what happened is that, as I said earlier, we obtain these enfolding artifacts because of we are violating the physics of the Nyquist theorem. So to solve this issue comes another component, which is the incoherent part. So what incoherent means is the data is acquired pseudo-randomly, and this can be done by using a non-Cartesian pattern, like here. Instead of having a straight line, as I was showing earlier, we can just have a pseudo-random pattern. And what this causes is that the image that we obtain is no more an image like the previous one that had enfolding artifacts. At this point, we have an image that has overimposed some noise to the image, so to the actual MRI. But what we want to obtain is an image that didn't have noise. So the first part has allowed, in any case, to accelerate the MRI. Now we need to remove the noise that has been overimposed. And for this enters in the game the transform sparsity. What this means, transform sparsity? Sparsity is the fact that the signal can be described by a limited amount of data, and most of those can be either zero or non-zero. And the term transform means that if we look, for instance, at our scene, at our image that we just obtained, and we draw a line across it, and we look at the intensity along this line, we would see that the value oscillates, so there is a great amount of noise. And the transform sparsity says that we could imagine to go to a different domain, like to a transform domain, for instance, the wavelet domain, and find a domain where it's easier to separate the noise from the actual signal. So, and that way can be done with wavelet transforms. So if we move to the new domain, we can easily separate, and for instance, by placing a threshold and understanding what is signal and what is not. But so we had accelerated MRI, and which introduced some noise, and this approach can remove the noise. But what happens is that at this point we need to introduce a way to decide which portion of the data can be removed and which should be maintained, since we need to set a threshold. And for this, the non-linear linear iterative reconstruction, the step, help us. So what happens is that if we only give importance to the transform sparsity, basically we are setting to zero all the image and we wouldn't see anything. Conversely, if we kept data consistency, what we would be doing is that we are totally trusting to the signal as it is with all its noise. So there would be an iterative approach where we kind of juggle between the data consistency and the transform sparsity until there is harmony between the consistency and the sparsity, and we finally can find our nice MRI that we would like to obtain. And this is done using an iterative approach and minimizing also a sort of loss function. So let's look at what are the main limitations of this approach. Certainly, initially, as I was saying, in MRI in clinics, they are acquired in a Cartesian fashion, whereas one of the requests was that in order to have an incoherent subsampling, we need a non-Cartesian or pseudo-random approach, which is not what is happening in clinics. And the sparsifying transform that are used sometimes cannot capture the complexity of all the organs. And because it's an iterative procedure and is an optimization, all the time at each data, each new volume, it's considered as an independent new volume, which I accepted, which is computationally expensive. And also,
it's okay, like the accepting thing can be managed by us. One thing I wanted you to repeat was, I could understand the other two limitations, but MRI in clinics follow mostly Cartesian sampling. How is it a limitation for compressed sensing reconstruction?
oh, because as you remember at the beginning, I was saying that one of the principles is to have incoherent subsampling, and that could be obtained by having a pseudo-random acquisition pattern, which is not which is violated if you do a Cartesian approach acquisition pattern.
Okay, so it is a conflicting situation.
Yes, because when you if you undersample with a Cartesian approach, basically it's like almost like you are acquiring straight lines in the K-space. And so one way could be to focus mostly at the center of the image and acquire only a few portion of the frequencies. Whereas if you have this sort of pattern on Cartesian, then what you obtain and pseudorandom, you can acquire multiple frequency and obtain an image that presents the incoherent subsampling we would like to have.
Understood. Yeah, great. And the straight lines in K-space mean that the K-space was not able to capture the contours and edges of the data. That's it. I'm just trying to translate things to layman language.
I think it's about the frequencies that are acquired more than, and those frequencies include information that relate to the edges as opposed to other frequencies that
Right,
are.
you explained about acquiring complete frequency in the fully this thing. Yeah.
Yes. Do you have another question?
No, please go ahead.
Okay, so, and what happens is that this approach is very sensitive to the hyperparameters. So if you have a poor choice, this leads to images that look either blurry or have artifacts, and they lose the details, or they are not really reconstructed. So in general, this is not because every time the reconstruction is a new optimization. What happens is that no prior knowledge is utilized, and this means that it doesn't really represent the way radiologists are reasoning. And so why would we use machine learning? And it's because the way of reasoning is much more similar to the way doctors think. The optimization procedure can be learned offline and then be very fast at inference time, and can be learned from training dataset. And also we can use the large amount of data, build very strong priors of the structures that we would like to reconstruct. And that makes it the processing scalable to big amount of data. So let us look how the reconstruction works from a mathematical perspective. It is described by is an inverse problem, which is formulated by using the forward model, which has this form here, where we want to learn is an inverse problem because we want to learn the reconstruction of this image X given some measurement Y in the presence of some added noise. And here A is a forward operator, which describes the physics involved in the MRI. So it is used to map the image space to the raw data and comprise the physics behind the image generation, which can comprise the sampling the Fourier transform in the case of the MRI. And if we were to use parallel imaging, where there are multiple coils used simultaneously, we have coil sensitivity maps. And the forward model is an ill-posed problem, which means that there might not be a single solution. If there exists, there might be multiple, and it's very difficult to find a solution. And often and this is quite difficult because we need to revert the operator of the acquisition. One way in which we could solve the problem is to introduce some heuristics about the statistical distribution of the signal. And if we had a normally distributed noise, which generally works well for the MRI, we can do a minimization of the least square errors between AX, which is our reconstruction, and the K-space data. And this difference here creates what is called data consistency. But if we just try to minimize this term of the loss, it would be easy for a model to overfit on the data. So it's as a generally is done for problem overfitting, to solve problems of overfitting. One way is to add a regularizer, but this altogether this creates what is in literature known as the variational model. But what we are introducing here is another problem, because we need to define what regularizer to use and what is the metric that the lambda that weights data consistency and regularization. And a way we could use to solve this problem is to introduce some image priors, or other approaches are mostly more deep learning, strictly in the deep learning sense, where we dump the data and we use let the network to learn what is the mapping between the data and our reconstruction. So in terms of deep learning based reconstruction, we have 4 main type of approaches. The first is image domain learning, then we have K-space domain learning, and cascade between K-space and image space, and domain mapping or automap. So recall that there is a relationship between K-space and image space, which is the operator Fourier transform. And what we see is that in image domain learning, what happens is that from starting from this undersampled image, the CNNs are used to obtain an image that looks like the reconstructed denoise version of the image. In a case of K-space domain learning, what happens is that we start directly from the undersampled K-space, and then the missing information of the K-space is introduced in K-space, and only subsequently we go to the image space. When we instead have an iteration of K-space and image space, there are some consistency terms that are introduced, and it formulates the forward problem we saw earlier. And usually there are also is almost a recurrent neural network approach between image space and K-space. And then ultimately we have a domain mapping, where we go from directly from the K-space undersample to the final image. And the mapping or the physics related to the MRI is not really, it's kind of neglected. So every approach, as you can imagine, has some pros and cons. In the image domain learning, what we see is that we are starting from an image that has been undersampled and presents already some artifacts. As such, the network has to learn what these artifacts are and try to solve these problems by denoising the image and removing these artifacts. On the other hand, it is very easy to interpret an image that looks like images that we are used to observe, as opposed to K-space domain learning, where data in K-space are very hard to interpret. So, but on the other hand, we are not using data that has been corrupted or distorted. So it has the probe using the real data without any corruption. On the other hand, we lose in understanding interpretability of the data. The cascade between K-space and image domain takes advantages from both approaches, but on the other hand, requires domain expertise, needs to formulate the forward problem, and it is somehow slower and computationally more expensive than the previous approaches. And ultimately, there is the domain mapping, which usually involves the introduction of fully connected layer to learn the mapping from K-space to image space. And it's therefore computationally not really scalable for if you, for instance, wanted to apply to 3D data. And also neglects the physics that has been, the knowledge that has been established about K-space and the image space, the relationship with the Fourier transform. So each approach, it's clear it has pros and cons, and in the work I'm continuing to describe will be, we follow approaches mainly on the image domain learning. So at this point that we have described all these approaches, it seems like we got to a point where we can say, yes, we are there, the technology is perfect, let's go and use accelerated MRI, deep learning for to accelerate MRI, and let's have it work. In fact, it's not quite yet ready, but it will be, and eventually. And what I need to say here is there is a general, it's necessary to claim a general warning about image translation in medical imaging, because this can be harmful and can provide clinicians with unrepresentative images. In fact, what happens is that many approaches that do image-to-image translation often are trained using distribution matching losses, like those that are used for generative adversarial networks. And and in general, because they are data-driven approaches, can cause distribution matching. So as a result, they can introduce information just to the resulting images just to match the distribution in the training data. An example is, for instance, the introduction of hallucination. So in this example, on the left, an image has been transformed into an image healthy when initially it was a tumor, when this brain MRI is being converted from a flare acquisition to a T1 acquisition sequence. And what happens is that just because in the data set, in the training set, there were no cases with tumor, the reconstruction of this image didn't present the tumor. Whereas when all the data set included some tumors, also the reconstructed image included a tumor. Here instead on the right, the study showed that for an image that was healthy, when also in the data set, in the training set, there were no tumors available, the image was reconstructed matching the target, which means without any tumor. But when in the data set all the images had a tumor, then the image the reconstructed image also showed the presence of tumors, which means that makes us understand how dangerous this can be, because we can provide clinicians with images that are not correct. Another study showed defined this problem to the related this problem to the instability of image reconstruction models. And what they did, they engineered some MRIs, some data, and introduced, and then they observed that the reconstruction model couldn't again reconstruct this unusual text. In one of our works, we showed that we refer this problem where some features disappear as the false negative adversarial problem. The false negative feature problem, where basically what happened is that during the Fast MRI challenge, which is a very famous challenge, happened last year about fast reconstruction of accelerated MRIs in the knee. What happened that the best as well as the worst models in the ranking found difficult to reconstruct some very small features which are not rare, but they are very significant for management of patients, especially in cases like the osteoarthritis. For instance, here we have the a meniscal tear that is lost during the reconstruction. And in the study that we proposed last year, for instance, we show that we can utilize robust deep learning to prevent this problem. That's why we call it the by using adversarial robust training. So what we did here is we first introduced through adversarial attacks some synthetic features that are difficult to reconstruct from the reconstruction network. And when we identify these features, then we have a second step of robust training where the network over-penalize errors when they are done in the reconstruction of these features, these small features. And what we observed is that by using this approach, the network tends to better reconstruct features also when applied to real MRIs. So here, for instance, we have a difference map between the reconstruction with our robust training in place and without. And the arrow points to a difference, which is this region that contains some femoral lesion. What happens is that the improvement of image reconstruction is very unactive, again, topic of research. And the problem is, could be partially also assigned to the fact that the evaluation metrics of the reconstruction are not capable of capturing diagnostic abilities of the reconstructed images. And this makes it necessary to find new metrics that can help to analyze the models and make the deployment in clinic safe. So while we improve the image reconstruction, we can also stay on the safe side and think about a way to restate the problem for accelerating MRIs. And one way is that we can think as acceleration of the MRI as a way to have new dedicated sequences. They can be acquired very quickly and provide support to the clinician with new quantitative biomarkers that otherwise wouldn't be extracted. And this can describe, for instance, volumetric estimate of organs, thickness of tissues, and they can be done at the quality that are comparable with MRIs that have been acquired at high resolution. And we call this problem a task-based reconstruction. And in the work I'm going to talk about, we perform both image reconstruction and segmentation simultaneously from limited number of measurements. So for the segmentation from limited measurement, we have three different options that we could follow. One is to segment an image that is aliased or distorted, or we could segment after we have reconstructed the image, or we could segment simultaneously with the reconstruction, which is the approach that we follow. In fact, we use the hypothesis that reconstruction and segmentation are somehow related and similar tasks. So that allows us to use the multitask deep learning theory to achieve reconstruction and segmentation at the same time in the image space. So what the approach that we propose, we called it TB-Recon, which stands for task-based reconstruction. And the architecture that solved this problem, it's an encoder-decoder network where we have one encoder and two shared decoders. So the way it works is that we start with this zero field MRI, where zero field comes with the fact that when we have undersampled the K-space, the values that are missing in the K-space are generally substituted with zero values. And then therefore it's called zero field. So we have this encoding path that presents residual connections, the residual blocks, which is similar to what happens in standard VNet architecture. So the shared encoder ends with a shared feature embedding. At this point, we have two decoders that are as standard in as is standardly done for encoder-decoder networks, is just a replica of the encoder. And there is one decoder for the reconstruction and one for the segmentation. And they are identical, they only differ for their output, which is linear in the reconstruction and softmax activated in the segmentation. Softmax, because we have a 5-class segmentation problem here. So in terms of flow of features in the network, in terms for what is concerned reconstruction, we consider that because we are doing a sort of denoising problem, so it is quite important to have features flowing from the encoder to the reconstruction decoder. And so we have this. Yes?
One more question. In the paper, you mentioned about using residual connections versus using skip connections. Why did you go for skip connections?
You mean between the encoders?
Yeah, between the
encoder. Yeah, I was just going to say. So for the between encoder and the encoder and the reconstruction decoder, the reason why we have this skip connection is because it acts as a denoiser, so it helps to pass the identity function, so it's easier for us to denoise the image.
Right.
But the reason why there are no skip connection between the encoder and the segmentation decoder starts from the intuition that the image that we have inputted, which is the zero field MRI, is losing all the sharp details that we would like to use for the segmentation. So since in the reconstruction we are introducing these sharp details to have a sharper MRI, the intuition is that the reconstruction path will have a better representation of the features of these details. Therefore, we can pass those features to the decoder of the segmentation. And this is why we have what we call inter-task skip connections, where the features from the decoder of the reconstruction go to the segmentation decoder. Did I answer your question?
Pretty much. Yeah.
And whereas if along the encoder and the decoder, there we have skip connections because residual connection, because we kept as a backbone like the configuration of a VNet, which has residual connections. So what we notice is that these inter-task skip connections help to facilitate the flow of features between tasks, as I said, and better improve the reconstruction and the segmentation. And this is a view, global view of the architecture. So the network is trained end-to-end, and because, as I said, we do multitask problems, so the loss function resemble the multitask approach. We have a reconstruction term and a segmentation term, and alpha weights the two tasks. What we notice is that weighting the two tasks equally helps both tasks, arguably because the segmentation requires improvement in the reconstruction, and on the other hand, improving the segmentation somehow forces the reconstruction to be sharper, so you can include all the details that are needed for the segmentation. And then the reconstruction, both reconstruction and segmentation have multiple terms. There is a structural similarity and mean absolute error that for the reconstruction, and dice and cross entropy for the segmentation. And because we are mainly, yes.
Francisco, yeah, I was curious why you use an inter-task skip connection since we have a shared encoder already.
Yes.
Since we have shared encoder, the information which is needed to be captured will be done at the shared encoder, right? So why did we go with inter-task skip connections?
So,
Is there any?
so initially there was that intuition that I was saying that the fact that the way the feature would be in the encoder were not super representative of the details that were needed for the segmentation. And you'll see later in some of the experiments, and this actually it helps because if we remove these inter-task skip connections and we connect the encoder with both the decoders, the performance of the segmentation drops drastically. So,
Okay, thanks.
so thank you. Initially, it was just some sort of intuition, and then the experiment kind of agreed with the intuition, which was nice. And thank you for the question. And because we want to make the segmentation the primary task, then we monitor the dice similarity coefficient. So besides the regularization that comes from implicitly from using multitask learning, we also use the early stopping and dropout. So let's look a little bit at the data that we utilized. The dataset comes from a publicly available dataset, which is called the Osteoarthritis Initiative dataset, which is a multi-center longitudinal multimodality imaging study, which comprises mostly of musculoskeletal MRI and X-rays from a cohort of about 5,000 participants, which were screened over about 100 months. And of the big data set, which has different type of acquisition, we decide to utilize high resolution 3D MRIs, which are particularly suitable for tissue for visualizing tissues like the cartilage. And this acquisition is called the double echo steady state. I won't go in details as I'm not an expert in the acquisition procedure. But in terms of the size of the data set, we have data from 87 participants that were related to 2 different time points. And the data set came already with a data split that was done in a way so that there was no leakage of patients across the data set. And this data set was also utilizing a cartilage segmentation challenge, which was the International Workshop of Osteoarthritis, and they utilize the same data split. So it's a good way to also compare the performance of our method against other approaches that segmented the same tissues in a standardized way. So I spoke about the image reconstruction, and that's the tricky part, because so far I spoke just about high resolution MRIs in this dataset. Is there a question?
Yeah. From chat, Geetanjali is asking, what are the data sets that have been used? So I guess we have covered that already.
Oh, I was just saying, yeah, we use this data set that comes from the Osteoarthritis Initiative. And it's publicly available. I think that it's enough to go on the website of this data set and just register, and you get a link to the data set. And it's an incredible source of information for the musculoskeletal domain. So I highly recommend it. There is a lot of research that is done in that domain using this data set, and still the disease isn't fully discovered. So there is lots of work to be done.
Right. Great, thanks.
So,
I had actually a doubt in the previous slide.
which one? This one?
No, in the loss function.
Oh, yes.
Yeah. Actually, the SSIM is a evaluation metric, right? So actually wanted to know what effect did it have on the the loss function, because I've always heard that SSIM is a evaluation metric, and I've never heard it is used in the as a loss function.
Oh. So yeah, it's true. It is used also as an evaluation metric. Probably the conventional method has been to use it as an evaluation metric. But I think that recently in image reconstruction has been used a lot in as a loss function. So what happens is that if you just use a loss function like mean absolute error or mean square error, images end up being quite blurry. So the structural similarity helps a lot in maintaining the structures in the images and make them really more resembling the human perception. Is it a question? No. Okay. I think I can continue.
Yeah, yeah.
Yeah, please continue. Did I answer your question, by the way? Do you have any other question? Okay, thank you. So for what is concerned the creation of the data set, so since the data set comes in with a fully sampled version of the data, we had to create our own version of undersampled data. And we used the fact that we had the relationship, the Fourier transform between image space and K-space, which allowed us to go back to the K-space. At this point, we applied something which is called variable density Poisson disk undersampling mask, and allowed us to undersample the K-space and at different acceleration factors. And therefore obtain then with the inverse Fourier transform the data set that we use as input to our data set. What I'll show here in this animation is how the image degrades with the increase in acceleration factors. As you can see, if at 2 acceleration factor, the image seems almost like a perfect image. When we reach 24 times acceleration factors, all the details have been lost. And here is another schematic of our approach. So we ran many experiments with different acceleration factors. And we also compare against a number of comparative solutions. So one approach is using an approach, again, end-to-end, but we had two different decoders, two encoders and 2 decoders, and both were trained in cascade. So we have one encoder that is a decoder to reconstruct the MRI, and then the reconstructed MRI enters in another VNet that segments the MRI, and they are trained end-to-end, the same loss function as the one for our TB recon. And then we had another approach where we have a cascade of 2 networks trained separately. We have one side, the segmentation network, which is trained to segment fully sampled MRI, and is a VNet, the segmentation network. And then we had reconstruction approaches, and we used 3 different reconstruction. One was the compressed sensing approach, which is what I described at the beginning. And then another approach is deep learning based reconstruction in 2D, so with a UNet, and then a 3D reconstruction. And after we do the reconstruction of the undersampled data, which is also sort of denoising, the denoised image is fed into the segmentation network to produce the segmentation. So now that I showed you all the setup and the data, do you have any other question? Otherwise, I will continue with the results.
I guess we can continue to the result.
Okay. So here, what I'm showing you is, and it is an example of segmentation performance at different acceleration factors. And I'm showing a point-by-point distance surface distance between the ground truth and the segmentation that we obtained. And what you can see is that a different, even when only a fraction of the K-space is acquired, the die score of that specific volume has dropped only, for instance, of 2%, which I think it's great, considering the difference in the data that was inputted to the model. Here, what I'm showing you is that although the reconstruction we said is an auxiliary problem, it's still good to show how the reconstruction looks like, since one of the warning I expressed at the beginning, not a long time ago, was about the fact that some important features are lost during the reconstruction. But here we can see that bone marrow edema, it's still visible after the reconstruction, even if the input was 12 times accelerated. Here is another example of the segmentation. And what we can see is that both at the patella, but the trochlea, the approach of TB-Recon gives a better segmentation of these tissues, which are highly challenging, as we can see from for the other two comparative approaches. And as we can see also, even if the dye score might change of 2 points, sometimes the changes might be subtle. So this shows a little bit that the metric is not really strong to demonstrate when there are big sections that are missegmented, or if the areas that are not segmented are important for a clinical reason. Oh. Here, instead, what I'm showing is the importance of having the reconstruction step in place and the intertask connections with this ablation study. So in this case, when I say no MRI reconstruction, means that our network was trained to go from an undersampled MRI, zero field, therefore, to a segmentation map. And if at low acceleration factor, the performance is pretty comparable, when we have higher acceleration factors, we can observe that having a reconstruction step in place, it's crucial and allows stability and higher performance. In fact, some tissues were not basically segmentable without the reconstruction in place. When instead I say here naive, is basically I'm replacing the intertask connections with skip connections that are from the encoder to both the decoder, as was asked by the previous question. And what we can see is that, again, without these intertask connections, the performance tends not to be possible in some compartments. And the models were, we did all our best to have them optimized, to have them all segmented. And again, this I think is a proof that the intertask connections were fundamental to obtain the result that we obtained in this problem. So as I mentioned, that we used the same dataset that was used in a segmentation challenge. And because we utilize exactly the same data split, we can compare our performance with the other approaches. But what is important in this table is that while the approaches that were participating to this challenge were trained on fully sampled MRIs, and also sometimes were also ensemble of multiple models, our approach here obtains as input, uses as input a 12 times undersampled MRI and segment the image at a competitive segmentation with the other approaches, which is very interesting and I think encouraging for us. Here I show in terms of image reconstruction metrics. So I report the structural similarity, as you were correctly mentioning earlier, and also another classical metric to use is the normalized root mean square error. And again, it is what we are proposing had a better performance. So it's time to express the main limitations of this work, because even if performance was great, again, as everything, there are some limitations. And some limitations come from the data set that was utilized, since we are using data that is, the OAI data set, as I said, doesn't have the raw data. So using just a Fourier transform to go back to the case space does not necessarily give the actual raw data. And also, because we are using this relationship to go back to the case space, we are forced to treat the data as if it was a single coil acquisition, which is not always the case in clinical practice where we use multi-coil. So this is part of the future direction of the work, which will be trying to have prospective data and multi-coil data and use therefore the real case space. And so to conclude, let's go back to the initial motivation of the work. So we've seen that the MRI requires some acceleration, and this is inherent to the process in which the acquisition is happening. There are many options out there. For deep learning is certainly one of them that is a great solution for obtaining faster MRIs. And but we also seen that deep learning can be dangerous, and we need to be careful with the power of deep learning, and we need to find solutions to guarantee realistic and diagnostic images. Meantime, there is a task-based reconstruction that I just spoke about, and we introduce, and we truly believe in its power because it's a promising tool for accelerated MRI and potentially obtain a very dedicated acquisition, which could take advantage of very high acceleration factor. And in this direction, we propose DB-Recon, which is a task-based approach for cartilage segmentation and image reconstruction. And we observe the effect of inter-task skip connection and generally the multitask approach on the two problems. So some final food for thoughts, which is the importance, in my opinion, to highlight that for crucial deployment of, for safe deployment of deep learning in image reconstruction in clinics, we certainly need to understand what are the responsibilities that could be on us, but also in who deploys the algorithms, and this is further compounded by the need for more metrics that could safely evaluate the final product, because obviously we don't want to have a metric that tells us that we have an amazing and perfect image, but then in reality the image is not diagnostic because the tumor was not reconstructed. So reliability and trust on the evaluation metric in this sense must be key. So this is the link to the reference to our paper, which can be, feel free to read it, and if you have any question, I'm happy to respond to emails or anything. And here's some references and a little bit more, which I didn't introduce inside the presentation. And as you can imagine, the literature is very vast, and I apologize if some work have been are present in this list. So I would like to thank ultimately you for your attention and for being so kind to invite me today, and also my research team and all the funding sources. And I'm happy to continue discussion if you have any question. Thank you so much.
That was a great presentation. One major question I have is like how much domain knowledge was needed, because when I was trying to read through the paper and analyze the result segment that you explained so beautifully, I could not make much sense out of it. So how much prior domain knowledge is needed to work in medical imaging?
Okay. I think that these days with when it comes with using deep learning, sometimes there is not really need of domain knowledge. Probably in every problem is a data-driven approach, right? However, there is an aspect which is having access to knowledge, like knowing what you're doing is always kind of a plus and helps you a lot. And being in an institution like UCSF, which is primarily a medical institution, that definitely helps a lot, because for instance, I'm not the expert in the acquisition part, or but I can go and speak directly with expert in MRI physics, and they would really direct me in the right direction if I am making wrong assumptions. So I would say that having domain knowledge helps in making the correct assumption when it's necessary.
Right. Where we have a few questions in the chat box. I guess I'll have to read them out. First one is from Vikas. It is a generic question that medical image detection requires high level of accuracy. Any general tips on how to improve the accuracy?
For the segmentation?
It says medical image detection requires high level of accuracy. Any general tips on how we can improve the accuracy?
It's a very vague question. So when you mean detection is like an abnormality detection, for instance, in an image, or I think there are lots of methods that at the moment that have been kind of deployed. I think that now there are works where now also transformers are being utilized for object detection, so they could potentially be also employed, and seems like they've been working in a fantastic way, at least in other domains. I haven't seen them apply to medical imaging yet, and I think it's just a matter of weeks, of months, and then we'll start seeing them also apply there.
I recently read one ECCV paper on anomaly detection medical imaging, and they extensively used the concept of attention to, like, the paper was called CAVGA, convolutionally something guided attention, and they used attention. So people have started using attention, and there was one other question. It says, a bit off topic. In the beginning of presentation, you did mention that nerve branching points can be used for retinopathy stage identification. Can you elaborate on that? I have been working on glaucoma detection and thinking of analyzing blood vessels.
Okay, this is interesting. It was part of the work I did during as part of my PhD project. So basically, during my PhD, what we were doing is to analyze the curvatures and the angles at the branching points of vessels in fundus photographs, and see how this curvature or branching angles would change over time in patients, and try to see how this was correlated with the progression of diabetic retinopathy. So this was what I was referring to. So in practice, there was an example of, I saw it like as an example of using the segmentation as a starting point for subsequent analysis. So is there a particular question you would like to ask about that?
Yes, no, they have just mentioned this stuff that I read out, nothing in
Okay.
particular.
But feel free to send me an email. We can discuss about it offline. We're very happy.
I guess these were the questions.
Hi, Francesco.
Hello.
Because this side, am I audible to all of you?
Yeah.
Actually, currently, I'm working in a healthcare domain, like past 3 years. So currently, I have done some projects on jaundice detections using deep learning, and as well as some X-ray imaging. I have done some projects and implemented that. But here, my experience was that I found disease is something changes with the ages. Okay, so that was something for example, if I will take up pediatric cases for jaundice detection, so it will be different. But if I will talk about adult, so it will be the different. So can because we cannot build a model for every ages. So can we can you give me or anything that will be great for me? Thank you.
Oh, that's $1 million question. So it is true. It's when we have a data set that let's say has when we have a model that is trained on pediatric patients, for instance, and then we try to apply to elder people, we always expect and it's justified performance, dropping the performance of the model. So what I know that there have been methods that have been tried, for instance, now in MSK domain, like where unsupervised domain adaptation could be a solution in that direction. So in theory, your network should be almost able on its own to adapt to what is the new situation. The point is that we are always talking about pathologies, and it's you always require some sort of interpretation of and explanations from the model to be sure that you are always looking at the right thing. Or does this
Hello?
give any? Do you have any? Does anybody here has an idea or an opinion about it?
Yeah, okay. So thank you. Actually, the doctor's team told me that we need a pretty much accuracy. So because something we are going to tackle with the human, right? So that is something they just, if you are sure about 100%, 99 or something, they are talking.
Can we
Hi,
assume?
Francesco.
Can we assume like a diverse data set would be a good solution to the problem of difference in images with age?
Is a question for me?
Yeah. So
Ah,
I'm
repeat again.
for Vikas' question. Can we assume that a diverse data set with lots of images from different age background would be the solution?
I would say that definitely having a bigger variety in your data will help. It's like the concept of when you do that augmentation, but also we cannot expect that every case is described in the data set. So the model should generalize as much as they can to be kind of deployable eventually. What do you think?
Thank you.
Yeah, so are we done with the questions?
Yeah, Francesco. I
Yeah,
have a
I'm done.
query.
Thank you. Thank you so much.
Thank you.
Here we go with the idea that reconstruction and segmentation are closely related tasks. So how can we evaluate that? Because how to evaluate that two tasks are closely related? That itself is a very, is there any work you are aware of that? Is there any experiment there?
So I think that it's there are some works where problems of regression and segmentation have been coupled, and they've been shown to improve the segmentation. I think that I don't want to say something wrong, but what comes to my mind is a variational autoencoder for segmentation that was probably won the Brad Challenge in 2018, probably, where again there is the segmentation that is coupled with the regression of the input image. And again, the problem to some extent is very similar, because you have, in this case, you, instead of having the reconstruction of the input image, we are denoising the image at the same time. So that makes the problem similar. And also they are related because there is a very close relationship between the image and we are reconstructing and the segmentation, because otherwise we wouldn't be able to do segmentation from that input image. If we use the fully sampled image and we try to segment, if they were not really similar, we wouldn't be able to, I would imagine. But
Okay,
estimating the similarity of the two tasks, I'm not aware of how that could be measured.
That itself is a very big question, very difficult question to ask.
Right. So I guess we are done with questions. It was so great hosting you, Francesco. We loved the presentation and the introduction to medical imaging. We could understand a lot of challenges, and we look forward to more work from you in future.
Thank you, and I look forward to